Hello everyone, my name is Aqib. Today I'll be talking about a numerical technique to solve some integrations which may not be very accessible by usual analytical techniques. So to this end, I'll be discussing Gauss Quadrature technique today, which will basically tell us how to integrate expression of this form -1 to 1 f of x dx. Now you must have realized that all your integrations may not be of this form. So although you have a function in here, but your limits might be something different, let's say from 0 to 2 or something like that. That is true, but every integration can be brought into this form by using some linear transformations. So for example, just to illustrate this, let me take up this integration. Let's say integral 1 to 3 x squared plus sine of x dx. Now clearly this doesn't fall into this, but as I said, we can do a variable transformation so that it does. So basically what I'm saying is you put x okay, let's say x prime equals ax plus b. Okay, in such a way you choose a and b in such a way that these limits become -1 to 1. So for example, I want x prime to be -1 when x is 1, so a plus b, and I want x prime to be 1 when x equals 3, so this is like 3a plus b. Now you can solve these equations for a and b. For example, in this case you get what do you get? So you can just add them up and then okay, let's subtract them. So you get a equals 1, b equals what, -2. Is it correct? Yes, this makes sense. So now using the transformation x prime equals x minus 2, you can get this thing into this form. And obviously you replace x by x prime here, and here dx prime and dx are same, but if a were something other than 1, then you would have to replace dx by dx prime, and then some quotient would come in here also. So this makes sense. Now basically what we have just shown, that any integration can be brought into this final form. Now it suffices to study this form then. Okay, now let us see what does Gauss quadrature tell us. So the usual Riemann integral is nothing but the area between the curve, that we all know. So basically you have your y-axis and your x-axis, and here is your x equals -1 and here is your x equals +1, and then you have a function running in between like this, and it has some area. Gauss quadrature technique tells us that there are some points which are known as weight points and some proper weights which can be found out in such a way that your integral I, which is nothing but this, can be written as the sum of weights and the values of the functions at those special points x stars. Now it may look daunting at first, but what it just means is that depending upon how much accuracy you need, you will first fix your capital N. So for example, you can have a single point quadrature, you can have 2-point quadrature, you can have 3-point quadrature, and so on, depending upon the value of n. And then you basically will just say that I is just the sum of weights and the value of function at that particular point. So let me show you what I mean, and also how we will compute these wi's and x stars. So basically f is known, right? The function is known, but you have to compute those special points x stars and also the proper weights. Okay, let us start. So let us start by one single point quadrature. I'm sorry. uh, okay, this just says that your I is equals w I is 1, so it doesn't matter. F of some special point x naught. That's what it is, simply put. Now clearly, mm, your there are two unknowns here, w and x naught. We'll need two equations to solve for them. So what we say is that let our technique be exact for integrations of linear functions and zero order functions. So which means that if this means that we assume integrations to be exact for x to the power 0 and x to the power 1. Now let me show you what I mean. What I mean is this: if it is x to the power 0, that is just a constant, if fx is some constant c, then I want to enforce the condition that this gives me the exact result. Now for this, your integration I is what? I is just minus 1 to 1 fx is just c dx, which is just 2c, right? And then our technique tells us that this same thing should be equal to w times f of x naught. Now immaterial of what x naught is, f of x naught is just a constant, so this means that this thing is equal to c times w, and this means that if you equate these two, you get w equals 2. Okay, this is fine. Now what about x naught? We still don't know x naught and we have one more unknown. So let this technique now be exact for x to the 1 also, which means that fx is equals x. Now if fx equals x, what will happen is that your I, your exact integral computed from here, is minus 1 to 1. Fx is just x dx, which is nothing but 0. And therefore your numerically computed integral w f of x naught is just w times, and remember w is 2, f of x naught, which is just x naught, right? Because f of x is x, so f of x naught is x naught, and this equals 0, so this means x naught equals 0. What it means is that your numerical approximate integral I is 2 times f of 0. That's it. And this is exact for linear polynomials, for zero order polynomials, and obviously linear polynomials. Now okay, now there are a lot of questions which we need to address here. First of all, why at all did we select these two, and why at all are we interested in polynomials? Your functions can be anything. Now you know that using Taylor series approximation, any function can basically be written as a series of polynomials. So if you are, so polynomials are in a sense basic building blocks of all the functions. Now if you are able to do this analysis for polynomials, then you can go on and extend to any general function. Second thing, it looks like we need these functions to compute the exact values and the numerical values. So where's the sense? I mean, it's very difficult to comprehend that why are we, if we know the function and we are finding the exact integrals, where is the approximation here? So the approximation will come in when your function is something else. So for example, let us take an example. Let's try to compute minus 1 to 1 x square dx. Now obviously you know the answer. You know that okay, this basically is x cube over 3, and you will put in the limits minus 1 to 1, and this will come out to be 2 over 3. This is good. But if I use my technique, then my integral I numerical will be what? This will be 2 times f of 0, which is 2 times f of 0 is just 0. Remember, x right? So this is 0, and this is obviously wrong. The reason is that our technique was just an approximate technique. It cannot do anything if the polynomial is of a higher order. It cannot do anything exact. Now this is an approximate solution. Um, Clearly this is off, and this makes us think that can we keep on doing this? Can we keep on increasing the number of quadrature points? So here I did a single quadrature point, so let us see what happens if I take two quadrature points. Now if I take two quadrature points, then my not f if I take two quadrature points, then your I could be approximated as w1 f of x1 plus w2 f of x2. Now there are four unknowns. If there are four unknowns, then you can basically satisfy this for x to 0, x to 1, x to the power 2 and x to the power 3. So what you'll do is you just start with the same premise. You take x to the power 0 and you get you basically find the exact solutions from here, and you find the approximate solutions from here. Now once you do that, you will basically end up with four equations in four area, and you will able to solve them. Now in this case it will turn out, I am leaving it as an exercise for you, it will turn out that w1 and w2 equals 1 and x1 is equals minus 1 by root 3 and x2 equals 1 by root 3. Now let us try to apply the same principle here. Does it work here? Before that, should it work here? Yes, it should work. And when I'm saying it should work, I'm saying in the exact sense. Will it give the exact answer? Because at the end of the day, it's a numerical technique. Finally, if I throw in a sine or cosine or logarithm or exponential, everything just goes off, because these are an infinite polynomials. You have to truncate them somewhere. You cannot have infinite number of quadrature points. In theory, yes, if you have an infinite number of quadrature points, you should be able to resolve it exactly, but you don't. Numerically, it's not possible. So therefore, what I'm saying is that even though you are not getting an exact solution, you will end up with a good approximation using this method. And the approximation you can the degree of the approximation you can manage by changing these points. Now let us see if it works. So clearly you have x square here, fx is f of x square, right? And if I plug in fx equals f of x square here in this expression, then let's see what I end up with. So I equals w1 is 1, f of x1, that is minus 1 by root 3. So minus 1 by root 3 square, right? Function x square evaluated at this plus f of x2, and you can appreciate it right now that it will come out to be 2 by 3. Now it's the beauty of this method, the main beauty of this method is that you are not only choosing your weights but also those special points at which this function is being calculated. So in this case, for a 2-point quadrature, what you are saying is that okay, there is an interval minus 1 to 1, but there are two special points which are located somewhat here and here, and they are symmetric of course, that if you calculate the value of the function at these points and you multiply it by some weight, then you end up with the value of the integral, and that is exact if your function is a polynomial up to degree 3. If right now if I throw in a polynomial of degree 5 or 6 or even a sine or cosine, then this answer will be off. But as I said, you can go on refining this and increasing the quadrature points to get better and better approximations. Now you don't have to repeat this calculation again and again. This has already been done. Now let me just show you what Wikipedia tells us about this. So let me open this and then let me just type in Gauss Quadrature. Okay, let's open the Wikipedia article. And then okay, it talks about all these things which we have discussed already. and then it basically tells you that okay, if you have number of points, then what happens. So I mean, for a single point quadrature, I'm sorry, for a single point quadrature, we already calculated this thing, right? That your spatial point is 0 and your weight is 2. For 2 point quadrature, I didn't calculate, but I told you that if you go and solve 4 equations for 4 variables with a technique very similar to what we did, you'll end up with 1 by root 3 and the weights are 1. And you can go for 3 point quadrature, 4 point quadrature, 5 point quadrature, you can do whatever you like. Now, again, I'll emphasize that this is at the end of the day a numerical technique, and the exactness which I was able to show in this video were only for the special cases through which it was actually derived. So it is being derived by assuming it is being derived means the coefficients and the special point, these are being derived by assuming the exactness of this numerical technique with polynomials of a particular degree, as high a degree as possible. Because if you look back, if you have a 4 point quadrature, you just have 4 points, you only have 4 slacks, so to say. You can't throw in infinite number of equations here. So you had 4 equations, so these are the ones we want to put in. And okay, if you put x to the power 4, obviously this will become 5 equations, 5 variables, and it will not, in general, it won't be satisfied. So at a given for a given quadrature technique, what you can do is you can go as high a degree as possible. Now, as you must have noticed by now that your -1 to 1 interval, that was just a convention. So for example, I can do the same thing by using an interval of 0 to 1, for example, and I can go through the same procedure. Just that -1 to 1 is a nice symmetric value, and you get symmetric quadratures like -1 by root 3, 1 by root 3, and symmetric weights and so on. So this is just if you want to say I mean a convention. Now you can obviously have your own quadrature formulas from 0 to 1 and so on. So thank you very much. I hope you learned a lot from this. If you have any questions, please drop a comment or email me and my email address is in the description. Thank you.